This will be the last video for this chapter, so this is one more example of using the kinematics equations, but I wanted to give you one that's a little bit harder. So that's what we're going to look right at next using the example problem involving the speeder and the trooper. Take a second and read the question. So if you haven't already, hit pause and read the question so you know what I'm talking about. The thing that should first jump out at you when you first read this problem is what's different about this one than the problems that we've done before is that this one involves two different objects. All the problems we had before only involved one, so that's going to change things a little bit for us. So the questions we're looking to answer is how long does it take the trooper to overtake the speeding car, and how fast is the trooper going when she overtakes the car? So we're going to, the hardest one is part A, so we'll spend most of this video figuring out how to work through and think through part A, and part B will be pretty easy once we've answered A. If you would like to, you can make yourself a diagram of what's going on. In this case, I actually think that a graph is a little bit more useful than just making a picture. So we're going to do a graph, and let's start it for the trooper. So the trooper is going to start from rest and is going to speed up over time. So I'm going to draw just like a little curve, kind of like that. The speeding car, on the other hand, is moving at a constant velocity. Now, the trick here, or one of the tricks, there's a couple, is that when the problem starts, we actually want to start at the time that the trooper took off. So when t equals 0, how far has the speeding car already gone? And if he was going 30 meters per second and the trooper leaves 1 second later, then you could say that the speeding car has already moved 30 meters. So instead of starting my speeding car down here, I'm going to start it further up on the x-axis to show that it had an initial position when the problem really starts. So he's moving at a constant speed, and we know that the trooper is going to catch him. So I'm going to draw something like this, where that red line should have a constant slope, and the blue line then has an increasing slope. So one thing that you can say is at this point right here, and this is the key to solving this problem, that at some point in time they're actually at the same position. So that's the whole idea that we're going to use to solve this problem. So here it is with a little better labeling. So we've got the initial position for the speeding car here, and then the linear graph for the speeding car like that, and then we have the increasing slope line for the trooper. So this initial position is going to make a difference, and then so is the idea that these are at the same position at the same time. So now we're getting closer to the math part. Here's the way that you have to think through this problem. Since they're going to be at the same time, or the same place at some time, and the first question actually asks us to solve for that time, we don't actually care what the position is. They didn't ask us that in the question. So if we can use an x equal equation for each of them, so if we have x equals for the trooper and x equals for the car, we can set them equal, and each equation will have t in it, and then we can just solve for time. Again, we don't need to know x right away, so we can basically eliminate it by setting the two equal. So let's start setting up the variables. We'll start with the speeding car. So the car is moving at a constant rate. Whenever something's moving at a constant rate, remember you have to use the equation for constant velocity. That's x equals vt plus xo. So we know the velocity is 30 meters per second. Question, is that average velocity or instantaneous velocity? Technically, in this case, they're the same because it's not changing. But when we look at our x equals vt plus xo equation, technically that's an average velocity, which is denoted by a line over the v. So that's what we're looking for. Here's something else that's a tiny bit tricky in this problem is the xo, and I mentioned this when we talked about the graph. If he's going 30 meters per second and the trooper doesn't start chasing him until 1 second later, he already has an initial position of 30 meters before the problem ever starts, before the trooper starts chasing him. That's when the problem really starts. So we're going to have an xo here of 30 meters. So our other variables, we've got v, xo, t, and then x. x here, we don't know what it is, but that's what we're going to set equal. So we're going to have an equation that's x equals, and we have it here that x equals vt plus xo, and I put the numbers in it here. So now we have an x equal equation for the speeding car. We just need to find one for the trooper, and then we can set them equal and solve. Here's the variables for the trooper. So the initial velocity was 0 because he starts from rest. They gave you the acceleration. We're looking for the time. Again, we'll do an x equals equation. They did not ask us about or give us the final velocity in the question, at least for part A. So we're going to use who cares for v for our equation. So here's our who cares equation for final velocity. We can go ahead then and put our numbers in, and then we have our equation here for the trooper. Now we'll set it equal to the equation for the car. So here we're going to work through setting the two equal. This was the equation that we had before for the car. This is the one that we had for the trooper. An annoying thing that you might notice, I'm going to go ahead and rearrange these variables. Notice that ends up being a quadratic equation. Yay, everybody loves solving the quadratic equation. Fortunately, I have a little quadratic equation calculator program that I will give you guys so that you can just put in the terms A, B, and C into your calculator, and it will give you the two roots, so you don't have to sit and solve the whole quadratic equation. Now, when you do this, you're going to notice something. One of the numbers is positive, one's negative. Well, obviously you can't have a negative time, so you can immediately eliminate the negative time and know that the time that you're solving for has to be 21 seconds. So now we've done the hard part. We found the time. All we have left to do is do part B, which is actually pretty easy now that we've answered part A. In part B, now they're asking for the final velocity. At this point, we know the acceleration, we already knew that. We just solved for the time. Now this is a case where we have to use the answer from part A in order to answer part B. There's no way around it. So we will use the 21 seconds. Starting from rest, looking for final velocity, and who cares about position. They could have asked us position if they were a part C or whatever, but in this case they just didn't ask us, so we don't care. So now all we have to do is find our equation, put our numbers in, and we're pretty good to go. So there's my equation. You can see my answer, 63 meters per second. And then, yeah, that's pretty much it. So part B a little easier than part A, but there's several things to think through in part A. A really nice thing about that one is looking at a graph and using a graph to help you visualize something. Also, the idea of setting two equations equal can be very useful in kinematics. So, oh, and how about the XO? You've got XO as an initial position. So whenever there's a difference in position between two objects, that's when you use that XO. Otherwise, you don't ever need to, because if you're in charge of the problem, you can just start XO at 0. So that's pretty much it for that one. And the rest of kinematics, things are not always going to be exactly the same from problem to problem. So I can't give you an example of every kind of problem you might see, but it's up to you then to practice, and it's something that will get better with practice. It really is a skill.